So we can ask, how did G do? Well, we need some way of measuring how well the greedy algorithm did. So we can say, was this good? And so we're gonna capture the goodness of an algorithm by something called the approximation factor. Okay, so our approximation factor, we'll use this function R for it. So I'll plug in the solution that the greedy algorithm gave us, so xg, and the approximation factor of xg is defined as the cost of xg divided by the cost of the optimal. All right, and here what do we have? We have it's 12 divided by 6, and that equals 2. Okay, so we know that the approximation factor for this particular instance and this particular greedy algorithm is 2, right? And that 2 means that the greedy algorithm gave us a solution that was twice as costly as the best solution, right? Two times worse, right? So if R of x equals 2, then x is 2 times worse than optimal. Okay, that's what an approximation factor of 2 means here. So it's not clear, we have no frame of reference for this yet. This is the first time we've ever asked this question. So it's worth asking ourselves, could we do something to this graph, to our instance, our TSP instance, to make the greedy algorithm perform worse, right? So for example, suppose I gave you an approximation factor of C, is there a way that you could modify this graph so that the greedy algorithm does worse than that approximation ratio, right? Gives us an approximation ratio greater than C. Okay, so we could say, question, could we do worse? Right? Could R of xg be greater than, say, 10, right? Could we get an approximation factor of 10? Could it be greater than 1,000? Right? And I hope it's clear that the answer is yes, right? We could make the approximation ratio as bad as we want. And so here's my claim. My claim is that for any c greater than 0, there exists an instance of the TSP such that R of xg is greater than or equal to c. So for every c, there exists an instance of TSP with greedy solution xg such that R of xg is greater than or equal to c. Okay, so here's my instance. Here's my instance of the TSP. And so remember, what does this mean? This means R of xg being greater than or equal to c means that the solution returned by the greedy algorithm is c times worse than the optimal solution on the instance. Okay, so here's my catastrophically bad instance, which shows you that that the greedy algorithm is a disastrously bad algorithm. Right? Notice that this statement above is a disastrously bad statement. Right? It means that the greedy algorithm has no way of guaranteeing anything good. Okay, so here's the graph, right? So again, here what's the cost of optimal? Again, it's 6, right? So if we draw the optimal tour, we do that, we do that, we do that, and we do that, right? Which again has a cost of 6. Okay. So now, how does the greedy algorithm perform? Well, the greedy algorithm starts, let's say it starts here. It'll follow that one. It'll follow that one. And then the only choice it has left is to go here. And then it's stuck doing that, taking this route here, which has a cost of 6 times c. So what's the cost of greedy? the cost of xg, and I'll draw this in red just to keep my color coding going. Cost of xg is equal to 3 plus 6 times c. Okay, and so by choosing c to be large, I can make the greedy algorithm perform as bad as I want, right? Because the greedy algorithm doesn't ever encounter that c, that cost of c, until long after it's too late. And so I could actually put that 6c, I could just as well put that 6c here, and it would be just as bad, right? Because that by the time it's down in that lower left node, it's too late for the greedy algorithm to make any changes. Okay, so here's the issue, right? We have this greedy algorithm we can make arbitrarily bad, and so it's just a formality at this point to say what's the approximation ratio associated with this, right? What is R of xg? Well, we know this is the cost of xg divided by the cost of optimal, so this is 3 plus 6c divided by 6. Well, this number here is clearly greater than or equal to 6c over 6. Which just equals c, right? Once we cancel those 6's. And notice the greater than or equal to comes from the fact that adding 3 on the left just makes it bigger, right? So we shrink it down to get it down to c, which means that we can make the greedy algorithm perform as bad as we want, because there's no upper limit on that number, right? I could plug in 6,000 in this graph, and that would give me an approximation ratio worse than 1,000. Okay, so what is our takeaway here, right? What's the result? The takeaway is that the greedy algorithm cannot be guaranteed to perform anywhere close to optimal, right? Or, you know, what we could say is there exists no guarantee of quality for the greedy algorithm. And I'll just be specific and I'll call it the local greedy algorithm for TSP. Okay, so it's sort of curtains on the greedy algorithm for the TSP from the standpoint of approximation ratio. So a critically important definition that we'll have going forward is the following. This is the definition of an approximation algorithm for a problem. So I'll walk through this definition. Here's how it goes. We say that an algorithm A, and we're always going to have the assumption that this is a polynomial time algorithm, because the whole purpose of this is to say, let's require speed algorithmically and then see how close we can get, or characterize how close we can guarantee. So a polynomial time algorithm, A, is called a C approximation, where C is some number. And in this kind of parlance, it'll be greater than or equal to 1. There will be cases when we think of it as less than or equal to 1, but here we'll be thinking of this as greater than or equal to 1. If every time you run the algorithm on an instance of its problem, the solution XA that it gives you back always has an approximation factor less than or equal to C. So what is a C approximation? It's an algorithm that runs fast and gets you within a factor of C of optimal. Right, so that's what this is saying. So C approximation is fast and within a factor of C of optimal. All right, and so what we've shown in this video is that the local greedy algorithm is not a C approximation for the TSP for any C. Right, and that would be the language we want to use. And it turns out that there is no polynomial time approximation algorithm for the TSP, right? And that's something that we'll show in the next video. But at the same time, there's many problems where approximation ratios actually do exist. And part of the purpose of this sequence of videos will be to showcase some of the good ones and then show how the proofs work that these things actually are approximation algorithms. One of the challenges in showing any approximation algorithm and proving an approximation ratio is that the very fact that we're working with problems that don't have polynomial time algorithms means that we can't just sit down and characterize, in an algorithmic way anyway, characterize the optimal solution. So we have to come up with clever arguments that say, despite the fact that we don't know what optimal is, we actually do know that we're within some reasonable constant factor of optimal.